Okay, let's start. So we're going to talk about the surface code again this lecture, but I want to introduce this paper. I think this is one of the best paper you can learn about the surface code, and very educational and also detailed. But first, before we start, I want, if anyone has any question about the surface code, I want to go through again, because we're going to talk about not only about the surface code, but also it's about the surface code, but not only about the error correcting code, but also about how you can use the surface code as if it's actual working quantum machine for quantum circuits. So we're going to talk about logical X, Z, and also CNOT gate, how to implement CNOT gate in the surface code, and also Hadamard gate. So if you have both, basically 4 gates, X, Y, X, Z, because Y is just X times Z, and the CNOT and Hadamard, basically that's the basic function, basic gates of the quantum computer, right? So is there any questions? Okay, you can Google this title to see the paper, the full text in the website, not in the internet archive. So, okay, I'm not expecting you to understand the entire error correcting scheme of the surface code, but so I'll briefly go through the first part and then go through the X and Z gate. The pictures are a little bit different from the last time I draw in my own Python code, but you have to map the previous picture from this picture. So in this paper, they always use this picture. So the black dots are the stabilizer, depicted as a square in the last lecture. It's a stabilizer qubit, and the white dots are data qubits, depicted as a circle in my picture. So you can see that there's the lattice structure of stabilizer and data qubit, and no 2 data qubits are connected directly, and no 2 same type stabilizers are connected directly. So always the stabilizer and data qubits are connected. There are in the inside 4 data qubit attached to 1 stabilizer, and 4 data stabilizer attached to 1 data qubit. So basically it's a surface. That's why it's surface code. It's a surface of this flat plane. And as I said, how they make one cycle of error correction is taking north, west, east, south. So any part of the stabilizer or the data qubit also, you take the circuit, the sender measurement on this direction, north, west, east, south. So it's depicted as ABCD here. So ABCD. For in terms of Z stabilizer, what you have is this circuit, and in the X stabilizer, it's this circuit. So look at the X stabilizer first, because if you look at the Z stabilizer, it might be a little bit confusing, because what you have seen here is actually the inverse CNOT gate, but not the CNOT gate from the measurement, from the stabilizer. So when you see the X stabilizer, what is happening is actually the sender measurement, because the black dot is the stabilizer that you're going to measure at the end. Here, measurement is here. So what you're measuring is the both product of eigenvalues on the data qubit attached to that stabilizer. So when you have a single data, single data qubit attached to the stabilizer, for example, A, you're taking, by the measurement, you're taking eigenvalue stored in this data qubit. But you have 4 data qubit attached. So there are all different, possibly different eigenvalues on this data qubit, on this X stabilizer. So when you read out of this measurement is 0, that means the product of eigenvalues on X gate, on X stabilizer, on these 4 data qubits are actually 1, plus 1. If it's minus, there are some odd number of minus eigenvalues in these 4 data qubits. And what happens to Z stabilizer is that you actually have the same, you should actually have the same picture. Instead of Cx, you should have Cz. But here, why it's actually inversed, because I'll show you in this picture. When you have a syndrome measurement on Z gate, for example, like this one, so this is the stabilizer, and this is the data, then you can actually change it into C0 gate, because a CZ gate you can implement using the C0 gate, because Z is same as HXH here, and then you can, or maybe well, let me finish this one first. You can have this one, or you can have different approach. But this one also do, but you have to go the long way. So you can also make it into H, Z, H with a C0 here. Okay, so CZ is actually can be switched because it's just the rule. When you interpret this CZ gate into matrix, it's a rule. Okay. So you can now change this into C0 gate, but now the control and the targets are reversed, and you don't have a Hadamard on the control. So the Z stabilizer is actually using that. So you can see that on the syndrome measurement qubit, you have the X gate acting as a target qubit, and this data qubit is acting as a control qubit. But still, we take the measurement on the syndrome on the stabilizer to see what the eigenvalues on these data qubits are. So the reason why not having the same type of picture is because first, it's when you actually implement the circuit or quantum computer or qubits like this, you don't implement CZ gate, because you want to keep the gate that can apply to actual physical qubit as minimum as possible. So you only want to apply the most necessary gate on the actual physical qubit. So all the qubits nearby are applied with the functionality of the CX gate, not CZ gate. And second, if you try to make the same type of gate, like H on the top and C control CZ gate or something like that, then you cannot make this number of gates on this entire circuit the same. So you need more operator in, well, maybe you get the same thing, but it's a little bit more complicated. But anyway, because you don't have a CZ gate, so you have to apply a little bit more on here. So it's getting a little bit complicated. So so you want to take as small number as possible, the number of gates to be as small as possible, and also you want to have a CX gate to be applied on a 2 pair of data qubit and stabilizer. So that's why you design the circuit in between the stabilizer and data qubit like this. And That's one cycle. That's the entire one cycle. So every time you take the cycle, you do this for every stabilizer. So you have a 8 sequence of the circuit of the gate to complete one cycle. So once you finish the cycle, as you can see here, you take the measurement. You get the readouts of all the stabilizer. So what happens is, okay, I'll show you the picture here. I'm basically going through the paper and the content of the paper. It's a bit long. It's very entertaining to read this, but I'm always thinking that if someone could explain the content of the paper first and then read it for next, I think it's better to understand. So anyway, so here is the surface code. This picture depicts the situation that progresses in time. So let's say the first layer right above here, above the surface code, is the time when you initialize the surface code. And you take the first cycle, 8 gates, and then you take the measurement. And plus sign, so, no, sorry, this one, not this one layer, this layer, these layer. Oh, no, so sorry. So, yeah. First, take the first layer here. So this layer. So plus sign means that your readout of your stabilizer is 0, sorry. So your readout is 0. And minus sign means that your readout is 1. Okay? So 0 means it's plus 1 eigenstate, and minus means it's minus 1 eigenstate. So it's not the eigenstate of a single data qubit again. It's not it's the eigenstate of entire data qubit measured from this stabilizer. So, okay, so I have this information. Okay, so everything that not in the black color, it's also in the gray color. You have always a positive plus depending on what the readout is. And okay, so let's assume that there's no logical gate applied. So I just waited. Okay, and then I take the measurement again. So I take another second measurement, which means that I take the second cycle to take an error correction, and then take the measurement. Okay, so most of the stabilizers don't change its readout. So for example, here on the X stabilizer on the corner, you have a minus readout, which means plus 1, which means 1 in the actual readout. And after another cycle, the readout is already again 1. So it doesn't change. That means nothing happened in nearby data qubit. However, you can see that in the black dots, the sign has been changed, which means the readout is changed. Here it's plus, and the next cycle it's minus. So it changed from 0 to 1. The readout has been changed. That means there is an error, unwanted error, occurred nearby data qubit of this stabilizer. Okay, so this stabilizer has 2 data qubits nearby. So in one of these data qubit has Z errors because X stabilizer detects Z errors. So what you do, and then you do this for every in this layer. You do this for every stabilizer. So here, this stabilizer has changed from plus to minus, and the next stabilizer, X stabilizer, has changed from minus plus. So you take a guess. Okay, so these 2 data qubits has been switched on. So what I mean by switched on is changing the sign, so changing the readout. Then I guess that the data qubit in between this X stabilizer has an error, Z error. So that's one guess. And there are another changes in that stabilizer. So I guess that there is X error in between these 2 Z stabilizer right here in this data qubit. And okay, so let's see. So in the real situation, if there is no measurement error, then everything could be fixed, right? But however, let's look at this one. I have I have X stabilizer changes its readout. Okay, if I have this if I have this X stabilizer turned on, that means one of the Z stabilizer, one of the data qubit has Z stabilizer here, here, or here. But then, okay, so in order to make this sense, I should either have all the Z stabilizer all the way up to here, or all the way up to here. That's not probable. Like if you have this, if you have this one of the Z stabilizer, then that makes sense because you could have an error. But in order to have this X error, you need, if you have to have these chain of errors, that's not that probable, and it's not going to happen that much. So you take that as kind of a measurement error. So you have to take the threshold when you take the measurement error or not. But this one, it seems like it's a measurement error, so you take that as a measurement error and so on. So and then here, now you can guess the next level, then the next cycle where the error occurred. So you keep measuring, you keep the information, the readouts, and then you're not actually, as I said, correcting the code on the way. You're just taking the information, and then after the circuit, or after all the quantum circuit is over, you backtrace that where was unwanted error occurred. So in this case, the measurement, the decision where the measurement error occurred or measurement or X or Z error occurred is done afterward, after all the circuit has been gone through. So that's how you take, that's how you interpret the result. Because if you know where the error occurred, then you can imagine that the circuit, your actual circuit was this, but since you have detected an error, that you can throw in that error as if it were there in your circuit, so that your measurement output, you can compare the actual measurement outcome with your calculation as if your error, your detected error, was in the circuit. So you can compare the result, whether your result is correct or not. Or is it that something that you expected or not? That's how you get the measurement error correction. But now, so what's good for if you have just error correction without any gate can be applied? Of course, sometimes people think about the quantum storage, the efficiency of the quantum storage, that you want your quantum computer just to store the quantum information. You want your quantum information to be lasted for the longer period of time. Then you could have the error correction code applied. But whatever you do, the quantum information is not stable as the magnetic information in the classical computer. So it's not the quantum storage, it's actually the quantum computing purpose that your error correction code is needed. So think about the X gate and Z gate. That's the most simplest gate that you can apply. So here is the X gate and Z gate you can apply in the error correction surface code. So here we have chain of X and chain of Z, and the loop of X. Well, maybe you can think of it as a chain of X too. But here you have X stabilizer on the left and right boundary. The X stabilizer boundary that has X stabilizer with the data qubit in between is called the rough boundary. And with the Z stabilizer is called the smooth boundary. So between these two rough boundary, you can have X chain. Okay, so connecting the one point to another, the data qubit. And this makes the logical X. And between two smooth boundary, this makes Z, logical Z. So it's not one Z or one X. It's the chain of X and chain of Z. And most importantly, it's about joining one side to another. Why does it make the logical X and logical Z? Because it does something that real X and real Z gate do on the single physical qubit. So what does X gate and what does Z gate do? Well, it changes the state, right? So whenever we represent a quantum state with a ket 0 and ket 1, there is no such thing as ket 0 and ket 1. It's not something that we can physically detect or see or realize. It's just a symbolic notation that we defined certain state to be called as ket 0 and ket 1, right? So what X does is that if we define to call some quantum state as ket 0, X does, it flips the bit side. It flips the, in the direction, in spin direction, whatever. So it flips the ket 0 state to ket 1 state. And what does Z stabilizer do? So once you have a ket 0 and ket 1 state, you can have a plus ket state, minus ket state, and that flip, Z gate, is something that flips the plus ket state to minus ket state. That's what X and Z gate are actually meant. So here, we're not talking about real quantum state stored in the data qubit. We are talking about some quantum state that has some eigenvalue, but the thing is, all the eigenvalues are either 1 or 0, so we consider the plus 1 eigenstate as a ket 0 logical state and minus 1 eigenstate as ket 1 eigenstate. So this X logical gate and Z logical gate does actually the same thing on these two logical state. So here is what I meant by that. So let's see, we have 0 logical state is considered as the logical 0. Okay, logical 0 quantum state, and 1 is logical 1 quantum state. What does X stabilizer do is changing ket 1 logical state into ket 0 logical state to ket 1 logical state, and vice versa. And you can define plus 1 so it looks like minus plus, but if you actually have a bar, it's a meaning of bar here. If it looks weird, I can make a bar a little bit bigger here. So this is considered to be simply the same meaning of the plus state of the physical qubit that has a same chance of having 0 logical state and 1 logical state, and minus ket's logical state is similar. And what the Z logical gate do on plus logical state is change it to minus logical state, and same and vice versa here. Okay, so whatever, whichever gate we apply, we consider it as a logical gate. If it performs the same changes like this one and this one, then we can treat that gate, treat that operation as if it's a logical X and logical gate. Now, we can even drop the meaning of the logical state, 0 plus or something like that. We can say that gate is X or Z as long as it satisfies these principles. Of course, if you apply twice, it has to be identity gate. And if you interchange the order of the application of action of this gate, then you get a minus. Then we can call this gate, whatever it is, as logical X and logical Z. So we can even interchange the meaning of X and Z because, the plus state and minus state are exactly same as 0 state and 1 state if you rotate your quantum state in the 45-degree angle. So we want to find which logical state, which logical gate has this identity. And in the surface code, these two chain of errors are actually having that principle. Look at these blue lines and red lines. It crosses at one single data qubit. Oh, and all the other data qubit has either X or Z, has no two gates applied. Only at this single data qubit they apply the X and Z applies at the same time. So when you apply the logical X, the chain of X first, and then chain of Z next, then on this data qubit you apply X first and Z first and Z next. But let's reverse the order. What would happen if you apply the logical Z first and then logical X? All the other data qubit doesn't care because they only have either either X or either Z applied. So changing the order of this chain doesn't affect the other data qubit. But on this data qubit, when you change the order, it changes the sign, right? It's same as changing, putting the minus sign on top. So you have in the entire space, all the data qubits are not affected, but because of this data qubit has been changed its sign, you have entire data quantum state in the entire data qubit changes the sign because every data qubit are tensor product of the quantum state on each data qubit. So these chains act as a logical X and logical Z. Now think about other types of chain. Instead of having this straight line, of course this is the shortest path, but how about if you go along the long track? So instead of taking, say, so chain of X error like this one, let's take a detour. So going above, and so not crossing this data qubit, having X here, 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 here. So as if you have a loop, not a loop, so it's a detour path like this one. Okay, even if you have a detour, now the fact that the two chains intersect at one data qubit doesn't change. So you still have the same effect on changing the order of application of a gate. So these detour can also be treated as logical X. Okay. Now you can think of this as another situation like, what if you have a detour but crossing this Z gate? So I'm not sure whether I can draw on here, or maybe I can. It's a highlight. Let me. Yeah, I can draw it. So let me draw something in here. Red. So what if I? Okay. Okay, the red. So what if I say I take these? Can you see? Can you see this one? Okay. So these detour like this. Okay, so I need to go along this way. Okay, so the last one is this. So I take a detour like this, but actually it's a loop with this one. But let's assume that I took these long detour of X chain. Okay. Then how many crossings? How many intersections with the Z chain? There are 3, right? So you change when you change the order of application of X chain and Z chain, there are 3 data points, data qubits affected by the change, which means it changes the sign. But 3 changes of sign means that it only changes once, because -1 times 3, 3 times of -1 multiplication is -1. So the overall, the effect doesn't change. We cannot see the difference between having this single X chain or these long X chains, right? And this principle that if you want to cross across this boundary, rough boundary, to that rough boundary, you always have to cross odd number of times of the Z change that is crossing the one smooth boundary to another smooth boundary. So because, well, it's basic fact that because of the topology of the surface or plane, you must have an odd number of crossings. Therefore, it doesn't matter whether you take the shortest path or you take a detour. As long as you go from one boundary to another, it acts as a logical X or logical Z. Or you can think of this way too. So if I took this path, like going through all the way from along this red curve, then it's actually same as having a loop route right here going through the Z stabilizer inside. And you're making this Z stabilizer, Z change, X change here. If you have a loop, let's say you just take this loop, okay? If you have a loop of X error, even if it intersects a single Z chain, this loop always has to intersect this chain of Z error crossing one smooth boundary to another smooth boundary even number of times. Right? There are always an even number of intersections. So when you have an even number of intersections, even if you change the order of the logical gate, you don't change the eigenvalue of the eigenstate. So your original state is unchanged. So the loop is not a logical gate. It's actually same as identity gate. And same thing for the half loop. If you're starting from one side of the rough boundary like this, and then you're ending at another, at the same rough boundary, then since you could, if there is an intersection between this half loop with the Z chain crossing one smooth boundary to another smooth boundary, you must have even number of intersections, so the eigenvalue is not changed. So half loop is not a logical X gate either. So that's basically the logical X and logical Z. So, well, this is about error correcting simulation. So skip this one. Okay, so now we're talking about. So, as I said, I think as I said in the last time, the surface code is so far the most ideal error correction code, but I'm not saying that surface code is easy to implement, because if you have a large surface code, yes, it's very easy to detect an error, but if you want to contain this big physical qubit in this big large area, you need tremendous amount of energy to make it cool. If you're using a semiconductor, superconducting qubits, then it's almost impossible to have this big area to be cooled down almost into absolute zero temperature. So, it's a side remark that in the superconducting qubit, it's almost impossible to have a large qubit quantum computer, but I think in the last decade, I think people are trying to think about other material to substitute the superconducting qubit, and there are diamond defects on. So there is a structure in the diamond that has a defect. So it's called what the name is, nitrogen defect, something like that. So in that case, you have more reliable material that can store the quantum information in a much more longer period of time. So in that case, you don't need that much energy or you don't even have to cool the material down to the absolute zero temperature. So in that case, you can have a more quantum qubits inside the device. So maybe if it's if that technology is developed so far, the surface code could be implemented. So every time people try to think about or research about the actual quantum computer, the hardware of the quantum computer, they are interested in whether that hardware or device has can have a surface code implemented. So having how the surface code is implemented is important. Knowing how surface code is implemented is important. So anyway, so except for having this long chain of errors and X errors and X chain and Z chain of its large surface code, there are other ways of making a X chain and Z chain. So by making a hole, so you're seeing the picture of a hole. So of course, we are talking about the actual physical qubit. There must be some boundary here, but assuming that this boundary is far away, instead of having long chain of X gate or Z gate, maybe I could have make an artificial hole inside the surface code and make a rough boundary inside the surface. So here, this rough boundary is actual boundary of the surface code or the layout of physical qubits. But inside, maybe I can take out one stabilizer, Z stabilizer, in somewhere here, and make it as if it's just artificial X boundary, the rough boundary. So this is called the Z cut because I cut the Z stabilizer, Z cut. Yeah, so Z cut. And here I can make a loop of Z gate, okay? The loop of Z gate. Now, this one acts as logical Z gate. You have to think about why. So you have X error. No, sorry, I keep saying error, but it's a X gate, okay, a chain of X gate and chain of Z gate, and it intersect at one data qubit. Okay? So as I said, how do you identify logical X and logical Z? It's only when you change the order to make a change of sign. So since we have only one data qubit applying both X gate and Z gate, when you change the order of the application of logical Z and logical X, it changes the sign, right? So you can consider this chain of Z gate as the logical Z gate, and this one already X gate because it goes from one rough boundary to artificial, although rough boundary here. So it's X gate here, logical X gate. So this is one way you can actually make a small X gate or logical X gate and logical Z gate. But you can make it large. How do you make it large? Well, first of all, if you want to make your chain of X to be large, meaning that you have many X gate inside your chain, then you can move your hole, the Z cut, far away from the X boundary. Okay? If you move your hole, then the chain becomes longer. What's good about having long chain? Because if you have a long chain, the chances that your X gate, logical X gate, fails is getting low because you are keep taking an error correction. So even if you applied X gate along this chain, you could have detect an error. You could have an error occurred. So even if you wanted to have X gate apply to all three data qubits here, because of X error, some data qubit don't receive X gate. So therefore, you don't have a full X gate here. But then, if you have a long chain of X gate, then you have less chance to have lots of errors along this long chain. So you could have detected the errors more efficiently so that you can correct it to get the actual X gate here. So, and also, you can make long jet chain by making a large hole. But how do you make a large hole? You just take away the Z stabilizer. right? Lots of Z stabilizer. If you take away, let's say, 2 Z stabilizer here, you get a little bit longer in the vertical side. If you take the one more out, then you get a different size and so on, right? So you can make it longer in any direction. So far it makes sense. I think just giving all the information fast, but I just want you to follow here. Ask me a question if you don't understand any part of this picture. So I just explained the pictures here. If you don't understand the picture, then you should ask. Yes. Oh, so this is about making an logical X gate, logical Z gate, without using the real X boundary and Z boundary. So here, this is real X boundary, the real boundary of surface code. But instead of taking the X chain from one boundary to all the way down to another boundary, I can make a hole, the artificial hole, artificial X boundary, to connect these one boundary of X boundary and other. So this is my X gate. Okay. So here, let's say this is our surface code, original surface code. The way you can make X gate or Z gate, logical X and logical Z, is connect the Z chain of Z gate from all the way from the top to bottom or left to right. Instead of having this long chain, you can have a short chain that acts just like the logical X and logical Z. How? You can make, oh, where is it? You can make a hole like this one. Okay, why it's not zooming in, out. Okay, so this, like this one, so I'm not sure why it's not working. Okay, so here, yeah, just make a hole to make the logical X, okay, and logical Z. Why is it logical X and logical Z? Because it changes the sign when it changes the order of multiplication, because there is one data qubit that is applying the X gate and Z gate at the same time. So Z3, X3 here. Then that's the omni data qubit that intersects. So you change the sign when you change the order of X gate, X logical gate and Z logical gate. Right? Okay. So any other questions? So it is the real key to the understanding of the CNOT gate, how to implement the CNOT gate to the surface code. So, okay, so the problem is now, how do you make a hole? So if the stabilizer were not there physically, then that is a hole. But you cannot take away the stabilizer away from the actual quantum computer. It doesn't really work that way, right? You're not physically removing the stabilizer. What you actually do, the paper explains the hard way of making a Z cut or X cut, and the easy way of making an X cut or Z cut. But here, I'll just explain the easy way. You just turn off the measurement. That's the easy way of making an X cut and Z cut. So here we have, this one is X cut because you remove the X stabilizer here. So in original situation, so this is, you can imagine that is some portion of the surface code, and there are many more qubits outside. But let's say I want to make an X cut here in this region. Now, I want to make an X cut around this X stabilizer. What I do is taking a one cycle, as if just I did for error correction, but I don't take the measurement here. I don't take a measurement here, as if it's not there, okay? So, okay, I could have not apply these C0 operator between this stabilizer and data qubit. But then I actually consider that as if it's not there. The stabilizer is not there, but it's the same effect. It's the same effect as I do all the C0 gates applied to this X gate and the nearby data qubit, but I simply don't perform the measurement on this X stabilizer at the end of the cycle. But if I do not take the measurement, what happens there? So remember, when you take the syndrome measurement, it's after you take the syndrome measurement that the data qubit is stabilized to the eigenstate of that gate, right? So if I don't take the measurement on this X stabilizer, all the data qubit, not only for this one and maybe other ones too, all the data qubit has nothing to do with the gate, the X gate on this stabilizer. So I just don't care, right? So I don't know so data qubits are not the eigenstate on this X gate anymore. So it's just same as it was not there, okay? Of course, because if I apply the C0 gate nearby data qubit with this X stabilizer, the state might change, but as I said, I don't care what actual quantum state stored in the data qubit change. All I care is what eigenvalue or in which eigenstate is these data qubits are stabilized. Since I didn't take the measurement, I don't care about the eigenstate on this X stabilizer. Okay? So not measuring this stabilizer is having nothing. Same equivalent to having nothing in here. And same thing for here. Okay? So it's called the easy initialization. So you can make a hole turning off the measurement. And now think about, you have to imagine that where your logical X and logical Z is. Now I'm going to imagine that my logical X is here and my logical Z is here. So nothing in here. So you need one X and one Z. Okay, so here's the question. As we talked about that this is X gate logical gate, and this is logical Z gate because it connects this Z smooth boundary, Z boundary to Z boundary. What if I take an X chain here? What if I take X chain here? Okay, so I have X chain here what if I take X chain, another X chain here? Can I take this two X chains as logical X gate? So this picture only says the one X chain, which is a loop, around the hole, so that's not a trivial loop, and chain, the line connecting the Z boundary to another Z boundary. Why don't we have X chain here? What will happen if I have X chain here? And considering these X chains and these chains altogether as X, logical X, what will happen? Yeah, sign doesn't change, because if I take these two loops as if there were another X chain, then this Z chain intersect at two data qubits. So the sign is changing at two places. So you have two minus appears when you change the order of multiplication. So you get no change. So having these two cycle as X chain is not acting as a logical X. So you should have one loop, not two loop. So, so the rest of the picture is now going to use this type. So having two or one hole, the X cut or Z cut, and one chain around the cut and the other chain connecting these two cuts. Okay, so let me show you the picture in the. So this one is a hard initialization. Yeah, like this one. Okay. So here in the gray color, it means that there's no X chain. So even if it's a cut, you're not assigning any Z chain or X chain here. But whenever you see this kind of picture now, you have to think about which boundary it is. So since this X chain is connecting these holes, that means these boundaries are X boundaries, right? These are X boundaries. Therefore, these are the Z cut, meaning that you have turned off or removed the Z stabilizer inside this hole. But around this hole, you don't assign Z chain, Z gate. But in this hole, you apply Z chain. And you can imagine that this is, well, in some sense, turning off one single stabilizer. But you can imagine that this entire loop is a big loop surrounding a large number of Z stabilizers. So you can also think about this arbitrarily size here. But I think the paper, it tries to get the picture as real as possible. So that's why they used this picture. So anyway, now since we are looking at this picture, think about moving your hole. So you can actually move around your hole. You can move your X chain and Z chain. So here you have a Z cut, which means that you remove the Z stabilizer. So I want to move my hole, or in the sense I want to make my X chain longer. Okay. Instead of having this hole far away from this hole at the first time, I want to initialize my hole here and then gradually move my hole up to here. So how do I do that? So the way I do is I simply take all the Z stabilizer, or in the Z cut, in the Z stabilizer, turned off to make a larger hole. Okay? And then I get the larger hole, and then I turn on in the next cycle these Z stabilizer to make it disappear. So whenever you take the measurement again, hole disappears. Okay? When you remove the hole, then any loop around that stabilizer is a trivial loop. So when you have a trivial loop, as I said before, it doesn't act like a logical X or no logical Z. So you can have the same effect having no loop around here, but you don't turn off the Z stabilizer at the end where you want to change, want to move your hole, move your cut. So except for these Z stabilizer, you turn on all the Z stabilizer to make your hole moved up to here. That way you can move your hole. And also, on the way you turn on and turn off, you want to create Z gate along this boundary, and then also you want to create the X gate along this data qubits so that you make a X gate longer, X chain longer. And also in the meanwhile, you actually make the Z chain longer, but the final configuration of Z chain is this one, so you are going to turn off this Z gate after all later. So after doing this, you get the longer X chain, but you can also do the same thing for the Z chain too. So I think there's a picture about how to make a Z chain longer. I remember there's something picture. Oh, not this one. So yeah, well, okay. So this is a picture, but anyway. So how do you make a Z chain longer? If Z chain is a loop that around Z cut, if your Z chain was this small in the beginning, how do you make it longer? You simply turn off the nearby Z stabilizer to make it longer. But when you turn off, you can simply turn off the 4 additional Z stabilizers at once, but then you have to make a Z chain longer at the same time. The problem is when you do it once, then there's a chance to get lots of errors. So you could do it one by one. For example, if your Z cut was here at the beginning, you take off or turn off the next nearby single Z stabilizer at first, and then take the error correction. So as I said, so this is the most important thing. When you try to increase your chain, the length of chain, every time you take a cycle to detect error, okay? That's the point. So just simply turning on and off of the stabilizer without detecting error leads you nothing, because the whole business is about I want to tracing all the errors, possible errors here. So even the making this hole bigger is business that we have to track the errors. So you want to increase the size of your cut one by one so that you can detect an error as accurate as possible. So you can turn off Z stabilizer here and here and here and here to make a bigger circle, bigger cut or bigger loop of Z chain here. And same for X cut. And then let's see. Here too. So as I said, you can move the hole one step at a time. So first, you turn off this Z stabilizer, make it one more bigger than before. So it's actually making a larger loop. But then the next cycle, so it's a 3-cycle step. So first you take this first cycle to make a hole, the cut here, and the next cycle you make a hole bigger, the cut bigger, and the next cycle you turn on the stabilizer that you don't want to be a hole. So you actually end up having the same effect of moving the cut in one step further. And along the way, you actually have to make additional, the X gate in here, X6 here, to make your X chain longer. Okay? So it was X3 that changes the sign when you change the order of the action, but now it changed to x6. So now this data qubit is where the sign is changing. So we talked about how to make chain longer and how to move your x cut or z cut. So now it's get really interesting. How do you make the C0 gate? So think about this situation. So I have, so let's say I have two cuts. This is Z cut. So I could have, this is considered as an empty cut, which means that I don't apply Z error or Z gate, logical Z gate here, but there could be a Z gate on this cut, but I don't apply the Z gate here because I just want 1x here. Okay, so I just want 1x. Now, what if I move my cut all the way in a loop and then coming back again here? So when I move my Z cut here, I'm making the chain of X gate longer along this data qubits, right? I get making longer. And when I finally came back, what I get is chain of X gate in a loop, in a trivial loop. Because inside this chain, all the Z stabilizers are active. We are measuring the Z stabilizer inside this loop. So when there's no hole, no Z cut inside the loop, it acts as trivial identity gate, right? So since we measure all the X stabilizer inside here, there's nothing happening here. We just consider the data qubits are in the same eigenstate with the same eigenvalue. So when you take the loop around any certain point, nothing happens. Okay? And same thing for Z. Well, in this case, let's assume that we have a Z cut, but we don't have X gate that connecting to these two Z cuts. But we have Z chain around this one Z cut. Now I want to loop around in the same way I did before, around one point. Just take a one loop here, and it's the same way I did it before. So you can have moving one hole at a time, or you could have this entire loop extended to all the way up to from the beginning. So either way, if you're coming back to original place, what happens is nothing, because you made a hole big, but inside the hole there's another island, right? So there's a hole, of course, there is a hole, but there's an island filled up with a Z stabilizer, which is still active, so nothing changes. So it's same as having the same Z cut in the beginning. Or if you're moving your cut by turning, just making it moving without changing its size, so you're moving at one step at a time, then once you're coming back to the original position, then all the Z stabilizers are still active and nothing changes, right? So having this loop or moving your Z cut around one point, you don't change the state. You don't change the state of Z gate and X gate around across this cut. And same thing for actually not only for the Z cut, also for the X cut. So now it gets interesting, really interesting when you have two X cuts. So, or not two X cuts, one X cut or one Z cut. So it also tied with the situation where you want to make a 2-qubit state. So how do you make a 2-qubit state in the surface code? If you have big surface code without any cut or hole, then it acts as one logical qubit. It's just one big logical qubit. I mean, one logical qubit consists of large number of physical qubits. How do you make it into 2 logical qubits? You could have 2 surface code. So as I said, it's not about a physical qubit, actual quantum state. It's about what you consider as a quantum state. So if I have these 2 Z cuts and 1 X here, then I could have a Z gate here on this 1 Z cut and X gate here, logical X and logical Z, and consider it as 1 logical qubit. And if I have, well, you could have a Z cut too, but in here it has an X cut because they want to explain the how to implement the C0 gate. Let's say we have X cut instead, away from this 2 Z cut. And in X cut, you have possibly the Z chain, which connects the Z boundary here, created by 2 X cuts, and then 1 X gate loop, which acts as a X logical gate. And in that case, you can consider this as 2 logical qubit state. Why? What do you mean by having 2 qubit state? It means that you can apply X gate and Z gate independently on 2 qubits. That is considered as the 2 qubit state, right? As long as you can apply X gate and Z gate independently to the quantum state, that is the 2 qubit state. There is no intersection between this XZ gate and this XZ gate. So you can apply independently, because if you change, what do you mean by independent? It means that even if you change the order of these 2 gates applied on this different logical qubit, you don't have a change in sign. So since there is no intersection between these 2 logical gates or chain of gates, there's no chain of signs. So therefore, you can consider this situation as having 2 logical states or 2 logical qubits. Now think about your loop. You want to loop your 1 of Z cut around the X cut of another logical qubit, like this one. Okay? And what happens is, since there was already a hole, the X cut here, when you loop around here, then it makes this X cut, the X cut, it makes the X error around X cut. It has the same effect of making an X chain around the X cut of the other logical qubit here. Why? Why is that? You think about how do you make the loop here. So you make a loop by making this X chain longer, right? So you end up having this picture, which has X chain along this data qubits, but you can split this data qubit chain of gates into 2 pieces. One is connecting this X boundary to this X boundary, this one thing here, and another thing is the loop along this data qubit. If all this X stabilizer around this chain loop of chain of X gate is turned on, if all the X stabilizer are active inside this loop, then this loop is just a trivial loop, same as identity gate. However, we turned off the X stabilizer to make X cut, right? So there's no X stabilizer here. That means if I take a loop here, you can have the same effect of having X chain here, because you can think of this as a following. So you have X chain here, big X chain, and let's suppose that this is this X chain. Let's suppose that all the X stabilizer inside big X chains are active, so they are all turned on. So it means that this loop is trivial, which means that this is just identity, same as logical identity gate. Now, you can have a same effect, having smaller X chain inside this X chain, big X chain. So having X chain outside or inside are the same thing, right? If your X stabilizer are all turned on. So having all outside X chain and having inside X chain has the same effect, because in the inside, all the X stabilizer cannot detect any error here, or Z stabilizer cannot detect any error inside. But now, if you have no stabilizer or X stabilizer inside here, then now the problem is you could have an X chain around this hole as non-trivial gate, but still there is a X stabilizer in between this small and large X chain. You can shrink this loop so that the effect of larger X chain and Z X chain are the same. They are the same effect on the measurement side of X chain, X stabilizer. So therefore, what happens when you loop your Z cut, one Z cut on one logical qubit around one X cut on the other logical qubit is that you create an X error, not X error, X gate here. So after you loop around here, you change the the state of the second logical qubit into something that apply the X gate, X logical gate on the second logical qubit. Okay? And let's look at the different situations. So the book, the paper explaining about 3 types of situation, and this it missing. Actually, I think it left for the readers to one more situation that we require to explain about the CNOT gate. But anyway, we have a similar logical gate, two logical qubits with 2 Z cut and 2 X cut. So here we don't have X cube. Is it Z cut? Z cut. It means yeah. You should have. We had an X chain, right, in the beginning. In here we had an X cut, X chain. But instead of X chain, we don't have an X chain. We just consider there's nothing, no gate applied. So we consider it as just identity gate. But on the second logical qubit, we assume that there is an X chain around one of the X cut here. So let's assume that I just moved my Z cut, one Z cut in the first logical qubit around this X cut. Well, nothing happens, right? Really, nothing happens. So it's just when I loop around this thing, I just turn on and off of the Z stabilizer along the way. That's all I do. But nothing happens because I don't apply any of the X gate or Z gate on the data qubit in the path, right? Because I started with the identity gate, so I'm not applying any X or Z gate along the data qubit. So it stays the same. So the first state and the last stage are the same. And let's look at one more step, one more thing, one more other situation here, and we can discuss about the CNOT gate. So you can see actually hear him. So we suppose that we have nothing here again. We should have Z chain here on this Z cut and X chain on this chain of data qubit here. We don't have anything here. On the second logical qubit, we could have X chain on this X cut, but we don't have that here. But we have Z chain connecting to Z boundaries. Okay? Now, I do the same. I do the same loop by changing this cut around this X cut. So you can see that I'm doing the same thing over and over, but the only difference is that where the initial situation that I'm starting from. Okay, so in this situation, the initial situation is this. So when I move my cut, what I do is I push the Z chain all the way across to here. Why? Because think about the situation when my cut is just before touching this Z chain. So I need to move my Z cut. I need to move my Z cut across this Z chain. So when I take the next step, then I need to turn off my Z stabilizer in the next place. When I turn off the Z stabilizer, then I need to move my Z chain, the chain of Z, into the next level in order to turn it off. So when I move my, like maybe I can draw in here. So when I move, can I? Okay, so when I move up to here, I need to turn off. So this is actually the situation that this is not I wanted, but okay. So let me go back. How can I undo this? Okay, so when I have here, my Z cut is right here. Okay, so when I Z cut right before, so Z cut it doesn't really go in the middle here. So Z cut is right here where its boundary touches the data qubit that had the Z gate here, and I move one more step. I want to move my Z cut to the next step. So maybe I do drawing. Let's do drawing here. So here is my Z cut right here, and here is the data qubit with Z gate because of the Z logical Z chain here, So I want to move it to I want to make the cut to the next cut. So how do I do that? I need to turn off the Z stabilizer. Z stabilizer was here, so let's say Z stabilizer in the square. I need to turn it off. But if I turn it off, then since I had a Z gate here, I don't detect any change in here. So in order to have this detected, I need to move my Z gate to be in here, in this data qubit. Okay. So if I just simply turn off, I just get rid of this Z gate. So turning off this Z stabilizer without doing anything else, then what I'm doing here is I just disregard the Z gate here, right? So I need to move it to the next Z gate in order to turn it off so that it has the same effect. So that's what I'm doing here in this picture. So it moves, and oh, sorry. So this one is not. So So we have Z chain. Oh yes, yes. So so actually this is Z cut. So let me be precise. So just I want to be precise. So we have data qubit, stabilizer, data qubit, stabilizer, data qubit. So it's X stabilizer, right? It's an X stabilizer here, and Z stabilizer. Since we are talking about an X cut, yes, that's how we have. So this one, this is logical Z. Well, maybe I just put the Z bar here, logical Z, on this data qubit. So these data qubits are applied with Z gate to make a logical Z gate. And where's my cut? I want to make a Z cut. So here, let's say this is my Z stabilizer. So let's say my cut is here, all the way just before, not just before, but let's see, X here, X here, X here, X here. So here you can see that there's a chain coming, but my Z cut, this is my Z cut from the first logical qubit. Is right here, just before it meets the Z chain. And let's see what happens in the next step. So I change my let's see, erase this one, cut to here, right? And then when I change my cut, I make this Z stabilizer, on the right hand side, this one, be active again. What time is it? Oh, it's almost time, sorry. So I should change, yeah, so when I do this, now I have this one. So, and then I want to push this in the next step, right? So I want to push this out. So what happens is, so in the next step, I want this. Sorry. I want this to happen, right? So this stabilizer, I want to turn off this Z stabilizer. But if you want the same effect of having one Z chain here, then you could have 3 Zs instead of 1 Z around this Z stabilizer. So this 1 Z, having 4 Z error or Z gate on this 4 data qubit is trivial, right? If you have the active Z stabilizer inside. No, that's what I'm just trying to make sense. No. So yeah. So when you have a when you have these 4 Z gates, then it's trivial because you turn off all the X stabilizer here, not the Z stabilizer. Sorry. So when you have all the 4 Z gates on here, then you have no turning on this X stabilizer. But in reality, you only have Z gate on this data qubit. But if you want the same effect of having one Z gate on here with the 3 data qubits here, then instead of having one, you should have go one loop around here, because it's the same thing. Having simple one Z chain here is same as having a detour around here. So that's what we are doing here. Since we are pushing this chain, the cut here, so we are pushing the chain into a detour, which doesn't intersect this cut. So all the way up to here. So I'll finish in 1 minute. So that's what we are doing here. So when we've done this so far, nothing changes along the way because it was identity again. So everything is, there's nothing, no gate applied. So you can actually consider this as having, instead of having these long loop, you could have same thing as having 3 type of chain. One is these small loop, and the other is these long loop, and the last one is this short length, short chain. So basically what happens is you have this small cut and a small chain and small chain here. So after you loop around this cut, you actually made additional Z error or Z gate on the first logical qubit. Okay? So this is actually the essence of making or implementing the C0 gate because of this identity here. So because of this identity, we'll explain next time, you can implement how you can actually implement the C0 gate inside of surface code. So it's somehow called, it's tied up with the mathematical terminology called braiding. So braiding is like you take the string and then you make it into tied together. So we'll explain these topics next time. So, and also if we finish the surface code next time early, we'll talk about the quantum annealing next time. Okay, so we'll stop here and see you on next Wednesday.